You hear her name and you think about radioactivity, glowing substances, Nobel Prizes. But nobody talks about what happened inside her head when she stared at a mineral that should not behave the way it did. April 1898. Marie Curie holds 100 grams of pitchblende in her hands. She has just measured it. The ore is 4 times more radioactive than pure uranium. 4 times. That should not be possible. Uranium is the source. Extract the uranium, you get the radioactivity. But this rock, this waste product from Austrian mines, this slag they throw away after pulling the uranium out, it glows hotter on her electrometer than pure uranium itself. Her instrument does not lie. The numbers sit there. 2.5 times uranium strength, sometimes 4 times. Something else is in there, something no one has seen. If you value documented scientific process and discovery history like this, subscribe. It is the best way to support our work. Also comment from which city you are hearing this from. Also, this script is researched and factual, using sources from Marie Curie's own doctoral thesis published in 1903 as Recherches sur les substances radioactives, her Nobel lecture from 1911 available through the Nobel Foundation archives, and the Comptes Rendus de l'Académie des Sciences, volume 127 from 1898, where the Curies first published their polonium discovery on July 18th. These are primary sources, her own words, her own data. Now back to the information. 63 different substances tested between January and April 1898. Only 2 emit rays, only uranium and thorium. But the minerals that contain them, pitchblende and chalcolite, they burn hotter than the pure elements inside them. The logic breaks. If radioactivity comes from uranium, then removing everything but uranium should give you the maximum possible radioactivity. But the ore beats pure uranium, every time. This is not measurement error. She has checked it. The electrometer Pierre built does not drift. The current it measures when pitchblende sits on the condenser plate is quantifiable, repeatable, undeniable. 4 times uranium. The mineral contains something else, an element no one has found. Her hypothesis forms not from intuition, but from elimination. She has tested the known elements. None of them do this except uranium and thorium. The ore contains both, but even combined they cannot account for the readings. Therefore, a new element exists. Not maybe, not probably, must exist. The numbers demand it. Separate the fractions by standard chemical methods, techniques used for decades to pull elements apart. Bismuth goes one way, barium another, lead and copper and arsenic each to their corner. But now they add a new step. After every separation, test the radioactivity. Measure which fraction carries the glow. The radioactive element will follow one path through the chemistry. Trace that path, find the element. This is the method. Radiochemical analysis. Use the radiation itself as the map. Acts like bismuth in almost every test, but it is not bismuth. Bismuth does not glow. July 18th, 1898. They present to the Académie des Sciences. The paper is 9 pages. Marie cannot present it herself. She's not a member. Her old professor, Gabriel Lippmann, reads it for her. They name it Polonium, after her homeland. Poland does not exist on maps. Russia, Prussia, Austria carved it up. 20 years it will stay partitioned. She names the element anyway. The first element ever discovered through its radioactivity, not through spectrum lines, not through crystallization color, through the rays it throws. Something else rides with it, something 900 times hotter than uranium. December 26, 1898. Second announcement. They name it radium, from radius, Latin for ray. In 8 months, they have found 2 elements that no one knew existed. The scientific community believes them, but chemists want proof. Not just concentrated fractions, pure samples, isolated elements, atomic weights determined. That means processing not grams, but tons. Marie writes it in her notebook on February 6th, 1898, with 6 exclamation marks. 44 Fahrenheit. Her hands are cold. The shed has no chimney. Fumes from the boiling acids hang in the air unless they open everything. German chemist Wilhelm Ostwald visits later and writes he thought someone was playing a practical joke. A cross between a stable and a potato shed, he says. This is where they will isolate radium. The Austrian government sends them pitchblende residue, waste from the Joachimsthal mine in Bohemia, now the Czech Republic. The uranium has already been pulled out. The residue is more radioactive than the original ore. The radium is left behind. They receive a ton, then more, then several more tons. Large sacks delivered to the courtyard. The process begins. Marie does the chemistry. Pierre measures the radioactivity. She dissolves the ore in acid, boils it in iron vats. Some days she stirs a mass with an iron rod nearly as tall as she is, standing over boiling pitchblende for hours. Her arms ache. By evening she's broken. The ore must be treated in huge batches. Dissolved, precipitated, filtered, dissolved again. Heavy elements are pulled out first through selective precipitation: lead, bismuth, copper, antimony, arsenic. 20, 30 elements mixed in pitchblende. Each one must be traced through chemistry until only the radioactive substances remain. At every stage, she tests the fractions, places them on the condenser plate, measures the current, follows the glow. Both precipitate as sulfates. But there is a difference, a tiny difference. Radium chloride is less soluble in water than barium chloride. When you dissolve a mixture of the two in water and let it crystallize, radium chloride comes out of solution first. The crystals that form early are richer in radium than the liquid left behind. This is fractional crystallization, a method known for decades, used to purify substances with slight solubility differences. But no one has used it to separate elements this similar, this rare, from a mixture this impure. 0.025 parts per million. She dissolves the 40 grams in the minimum amount of boiling water. 68 grams of water. Lets it cool. Crystals form. The first deposit contains 16 grams of barium chloride and 8.3 milligrams of radium chloride. The ratio has increased. The radium is now 0.05 parts per million. She takes those 16 grams, dissolves them in 27 grams of hot water. Lets it cool again. The second deposit, 6.4 grams of barium chloride, 6.9 milligrams of radium chloride. The radium concentration is now 1 part per million. She repeats. Third crystallization, 2.6 grams of barium chloride, 5.8 milligrams of radium chloride, 2 parts per million. Fourth crystallization, 1 gram of barium chloride, 4.8 milligrams of radium chloride, 4 parts per million. Each cycle increases the ratio, but the mass shrinks. She saves all the wastewater, evaporates it, recovers the barium and radium that stayed in solution, starts the cycle again, and again, and again. Decanting the liquid, drying the crystals, weighing them, testing their radioactivity. The spectroscope shows progress. Eugène de Marseille tests the spectrum for them. Barium shows a strong line at 4,554.2 angstroms. Radium shows a line at 4,533.3 angstroms. As fractionation continues, the barium line dims, the radium line brightens. When the barium line stops getting dimmer, Marie switches tactics. Instead of crystallization alone, she uses fractional precipitation. The chlorides are converted to bromides. Radium bromide is even less soluble than radium chloride. The process gains efficiency, but it still takes 3 years. 0.1 grams. She measures the atomic weight, places the pure radium chloride in a known amount, determines the chlorine content by precipitating it as silver chloride, weighs the silver chloride on a balance so fast it avoids moisture absorption, calculates backward to the radium mass. Her first determination, 225, close to the modern value of 226. The chemists are satisfied. Radium exists. It has an atomic weight. It is an element. She has proven it without ambiguity. Because polonium has a half-life of 138 days. While she works, it decays. Polonium-210 transforms into lead-206. The element vanishes as she tries to hold it. By the time she finishes a series of crystallizations, half the polonium is gone. Wait another 138 days, half of what is left is gone. She never isolates pure polonium. The Nobel Prize in Chemistry in 1911 cites her discovery of polonium and radium and her isolation of radium, not polonium. The element is too unstable, its decay too fast. No chemist of her time can hold it long enough to purify it. Now back to the information. She says there is an unknown element. That kind of reasoning, that leap from data to conclusion, is not faith. It is logic applied to numbers that will not bend. April 1898. She has the hypothesis. By July, she has polonium isolated enough to measure. 3 months from question to proof. The chemistry is not new, the methods are standard. Precipitation, dissolution, filtration, crystallization. What is new is the tracer. Using radioactivity itself to follow the element through every separation. This is her invention. Radiochemical analysis. It will become fundamental to chemistry. Every discovery of radioactive elements after 1898 uses her method. Radon, actinium, protactinium, all found by chasing the glow. She knows they are chemically similar. She knows she cannot just filter them apart, or distill them or precipitate one without the other. The periodic table shows barium at atomic weight 137. Radium, she suspects, is near 220, close enough in chemistry to behave almost identically, far enough in mass that their salts must have slightly different properties. She gambles on solubility. If radium chloride is even marginally less soluble than barium chloride, fractional crystallization will work. But the difference is tiny, The first few crystallizations barely shift the ratio. She starts at 0.025 parts per million radium. After 4 cycles, she has 4 parts per million. That is a 160-fold increase, but the sample has shrunk from 40 grams to 1 gram. She loses mass to gain purity. To get pure radium, she must accept that most of the material will be left behind in the waste solutions. She saves them, reprocesses them, feeds them back into the cycle. It is a loop. Crystallize, measure, dissolve, crystallize again. Every cycle must be perfect. One mistake, one contamination, one miscalculation in the amount of water, and the enrichment stops. Progress is tracked not by eye, but by numbers. The electrometer measures activity. The spectroscope measures spectral lines. Both must agree. When they diverge, she investigates. When they align, she continues. She arranges her radium fractions on these tables because there is nowhere else. At night, she and Pierre walk into the shed to see the samples glow. Faint blue luminescence in the dark. The radium excites the air around it. The glow is beautiful. She writes about this, too, the only time she allows sentiment into her descriptions. But during the day, beauty does not matter. The work is brutal. Stirring boiling pitchblende is physical labor. Lifting the iron vats, pouring the acids, filtering tons of precipitate. She is small, 108 pounds at her heaviest, 49 kilograms. The iron rod is nearly her height. She stirs anyway. The chemistry does not care about her size. When mechanical pressure is applied, the quartz generates a voltage. Reverse the process. Apply a voltage, the quartz expands or contracts. This allows precise measurement of tiny electrical currents. Radioactive substances ionize the air around them. Ionized air conducts electricity. Place a radioactive sample on one plate of a capacitor, apply a voltage across the plates, and a current flows through the ionized air. The size of the current indicates the strength of the radioactivity. Pierre calibrates the device against pure uranium. Marie's pitchblende samples read 2.5 times uranium. Later fractions read hundreds of times, then thousands. By the time she has nearly pure radium chloride, the readings are over 1 million times uranium. The electrometer is consistent. The method is reproducible. The numbers are real. The mental discipline required to perform thousands of crystallizations without losing track is staggering. Each crystallization must be documented. The starting mass, the amount of water used, the temperature of the solution, the cooling rate, the mass of crystals obtained, the mass of residual liquid, the radioactivity of each. If she forgets to record one step, the data chain breaks. If she contaminates one sample, the purity drops. If she rushes the cooling, the crystals form improperly and the separation fails. She cannot rush. She cannot skip. She cannot guess. This is the process. 1898 to 1902. 4 years. 32 scientific papers published during those years, either jointly with Pierre or alone. 32 papers while processing tons of pitchblende, while crystallizing thousands of times, while teaching at the École Normale Supérieure. To support the family, while raising their daughter Irene, born in 1897. The work does not stop. The isolation does not wait. The medical discovery comes from impure samples, from fractions that still glow enough to damage tissue. Pure radium will be more powerful. They know this. The numbers predict it, but the isolation is not complete. The discovery of polonium and radium, the isolation of radium chloride, the measurement of radium's atomic weight, the properties of radioactive emissions. The examiners declare it the greatest contribution to science ever written in a doctoral thesis. She is the first woman in France to earn a doctorate in physics. 3 months later, December 10th, 1903, she shares the Nobel Prize in Physics with Pierre and Henri Becquerel. The citation reads, "For their joint researches on the radiation phenomena discovered by Professor Henri Becquerel." Marie was almost excluded. The nomination initially listed only Pierre and Becquerel. Pierre refused to accept unless Marie was included. The committee relented. She becomes the first woman to win a Nobel Prize. The shattering of their voluntary isolation is a cause of real suffering, she writes. The press calls it romantic. A woman in a shed grinding tons of ore to find a magical glowing element. Fairy tales. Once upon a time, writes Le Figaro. But it was not magic. It was measurement. Tons of pitchblende, thousands of crystallizations, 1/10 of a gram of pure radium chloride. The numbers are recorded. The method is documented. Anyone can read the papers. Anyone can see the process. There is no mystery except the mystery of radioactivity itself, which no one yet understands. Isolates more radium. In 1910, she isolates pure radium metal, not just the chloride salt. She heats radium chloride in a vacuum with aluminum metal. The aluminum reduces the radium oxide to pure radium, a silvery white metal that tarnishes instantly in air. It glows. It generates heat. A gram of radium-226 produces 140 watts of thermal power from its own decay. It will keep producing heat for 1,600 years, its half-life. She measures its melting point, 700 degrees Celsius, or maybe 960. Sources vary even now. The metal is difficult to study. It reacts with air. It emits radiation constantly. Handling it burns the skin. She handles it anyway. The science requires it. For the discovery of radium and polonium, by the isolation of radium and the study of the nature and compounds of this remarkable element. She is the first person to win 2 Nobel Prizes, the only person to win in 2 different sciences, physics and chemistry. This record will stand until Linus Pauling wins in chemistry and peace. But Pauling's prizes are not both science. Marie's are. She is the only human to win Nobel Prizes in 2 scientific fields. This is the result of the mental process that started in April 1898 when she measured pitchblende and refused to dismiss the impossible reading, when she said the numbers demand a new element, when she built the method to find it, when she crystallized for 4 years to prove it. Her fingers are hardened. She carries test tubes of radioactive material in her pockets. Pierre did the same. They glow in the dark. She thinks this is fascinating. She does not connect the burns to the materials until much later. In the 1920s, she develops cataracts. Her vision clouds. She has operations to remove them. 4 operations. The cataracts keep returning. Radiation damages the lens tissue. In 1934, she is diagnosed with aplastic anemia. The bone marrow fails. Red blood cells drop. She is 66. She dies July 4th, 1934 at a sanatorium in Passy, France. The official cause is aplastic anemia caused by long exposure to radiation. Her notebooks are still radioactive. They are stored in lead-lined boxes at the Bibliothèque Nationale de France. To view them, you must sign a liability waiver and wear protective equipment. The pages will remain radioactive for 1,500 years. Polonium contamination, radium contamination, the glow she chased into her own cells. Fraction, following the numbers wherever they lead. It is not inspiration, it is not genius, it is discipline. Hypothesis from data, method from logic, isolation from repetition, thousands of repetitions. The radioactivity guides her. She does not invent radioactivity. Becquerel found it first in 1896. She does not invent chemical separation. Those methods are centuries old. She invents the combination. Use the radiation to track the element. Use the tracking to guide the chemistry. Use the chemistry to isolate the source. This is radiochemical analysis. This is her contribution. The method spreads. By 1913, researchers have found 30 radioactive isotopes using her technique. By 1930, over 50. Every transuranium element discovered in the 20th century uses some version of her method. Plutonium, americium, curium, named for her and Pierre, all found by following the glow through the chemistry. From their garbage, she extracts an element 1,000,000 times more powerful than uranium. From waste, she builds a new branch of science. The irony is direct. They throw away the most valuable part. She digs it out. April 14, 1898, she starts with 100 grams. April 20th, 1902, she finishes with 1/10 of a gram. 4 years. 1/10 of a gram. But that 1/10 of a gram has an atomic weight, a spectrum, a measurable decay rate, documented properties. It is real. It is proven. It is science. She will write about this with regret. The chemistry is correct. The method is sound. But physics defeats her. The nucleus of polonium-210 is unstable. It throws an alpha particle, becomes lead-206, and stops glowing. She cannot hold it. No one can. Not until 1902, when Willy Markwald in Germany isolates 3 milligrams. He thinks it is a new element. He calls it radiotellurium. 5 years later, chemists prove it is polonium. Marie was right. The element exists. But its instability makes pure isolation nearly impossible with the methods of 1900. Her office is preserved. Her equipment is in museums. But the shed is gone. The place where she crystallized radium thousands of times, where she stood in 6-degree cold with 6 exclamation marks in her notebook, where she stirred boiling pitchblende until her arms broke, that place is erased. Only the papers remain. 32 publications between 1898 and 1902. Comptes rendus. The Proceedings of the Académie of Sciences in Paris. Volume 127, page 175, July 18th, 1898. Sur une nouvelle substance fortement radioactive contenue dans la pitchblende, on a new strongly radioactive substance contained in pitchblende. Authors: Pierre Curie, Marie Curie, Gustave Bémont. 9 pages, the first announcement of polonium. The paper is in French. It has been translated. The data is clear. Pitchblende treated with acids and hydrogen sulfide. The sulfide is precipitated. The precipitate contains a very active substance along with lead, bismuth, copper, arsenic, antimony. The activity is measured quantitatively. The substance behaves like bismuth chemically, but it is not bismuth. Bismuth is not radioactive. Therefore, a new element. They propose the name polonium. If existence is confirmed, the discovery will be uniquely attributable to the new method of detection that Becquerel rays provide. This is the sentence. The method is new. The element is found by its glow. Not by color, not by flame test, by radiation. This is how science changes, not by accident, by method applied to data that refuses to fit. Sur une nouvelle substance fortement radioactive, contenue dans la pitchblende. On a new strongly radioactive substance contained in pitchblende. Second paper. This one announces radium. The barium fraction contains a substance strongly radioactive, entirely different in chemical properties from the first. The first is polonium. The second is radium. The activity of radium is even higher than polonium. 900 times uranium in the preliminary fractions. They name it for the ray. They do not have it pure yet, but they have measured it, tracked it through the chemistry, proven it exists. The isolation will take 4 more years, but the discovery is made. The element is real. The method works. Joliot for discovering artificial radioactivity. Irene was born in 1897 while Marie was processing pitchblende. She grew up watching her mother crystallize radium. She learned the method. She followed the glow. She won the prize. The second generation. Marie's granddaughter, Hélène Langevin Joliot, becomes a nuclear physicist. The third generation. 5 Nobel Prizes in the Curie family. Marie and Pierre in 1903. Marie alone in 1911. Irene and Frederick in 1935. The method passes down. The discipline. The refusal to ignore measurements that do not fit. The willingness to stir a boiling mass for hours because the data says something is there. This is the legacy. Not the glowing vials, not the martyrdom, the method. The polonium contamination, the radium traces, they sit in the paper fibers. The ink itself is contaminated. When she wrote down the measurements, the materials were on her fingers. The glow was in her skin. Every page she touched carries it now. 1,500 years of half-life remaining. The notebooks will outlast any building, any institution, any memory of the shed. The data will remain radioactive longer than the radium industry she founded, which collapsed when nuclear reactors made radium obsolete in the 1950s. Longer than the radium dial factories where workers painted glow in the dark watch faces and died from radium poisoning, licking the brushes to make fine points. Longer than the radium water craze of the 1920s when people drank radioactive tonics, thinking it was medicine. All of that is gone. The notebooks remain, the measurements, the proof. Pitchblende glows hotter than uranium. Therefore, something else is present. Isolate it, prove it, name it, move on. That is the process. Not faith, not genius. Discipline made absolute, measurement made sacred. Truth built from tons of slag and 1/10 of a gram of salt that glows blue in the dark. He watches Marie handle radioactive materials with bare hands. He tries to stop her. She waves him off. She's been doing this for 35 years. She knows the risk. She has seen the burns, felt the fatigue, watched Pierre's hands crack and harden. But the science requires contact. The measurements require handling. She does not stop. 1 year later, she is dead. The aplastic anemia is sudden, but the cause is not. 35 years of carrying radium in her pockets. 35 years of breathing radon gas in the shed, in the lab, in the institute. The decay products settle in her bones. The alpha particles destroy her marrow. The same radiation she chased into science has chased her into the grave. This is not irony. This is causation. The glow kills. She knew. She did it anyway. When they moved both bodies to the Pantheon in 1995, the caskets remained sealed. The radiation levels are too high. The French government considered the risk acceptable for a state honor. Bury them with Voltaire, with Rousseau, with Hugo. Let the woman who found radium rest among the immortals, but seal her in lead. The glow does not stop at death. Central Chemical Products. The company partnered with the Curies around 1900. The company marketed Pierre's scientific instruments. In exchange, they helped with the large-scale processing of pitchblende. André de Bierne, their colleague, adapted laboratory techniques for industrial scale. The company had facilities, had workers, had capacity to handle the preliminary steps. They dissolved the ore in acid, precipitated the heavy elements, processed the tons of material down to kilograms of concentrate. Marie received these concentrates and performed the final purifications, the thousands of crystallizations, the spectroscopic measurements, the atomic weight determinations. The company received a share of the radium salts produced. They sold them for medical applications. The partnership made the isolation possible. Without industrial help, processing multiple tons would have been impossible in the shed. But the final chemistry remained Marie's domain. The purity, the precision, the proof. Those required her hands, her method, her discipline. She was also the first to include laboratory work in the physics curriculum. Women students performed actual experiments, not just watched demonstrations. This was revolutionary in 1900. Female students touched equipment, measured results, recorded data. Marie taught them because she needed the salary and because she believed women should learn physics by doing physics, not by hearing about it. She taught during the day. She crystallized radium at night. She gave birth to Irene in 1897. She was pregnant during some of the early pitchblende processing. She took minimal maternity leave. The work did not pause for childbirth. The crystallizations had to continue. Any interruption meant starting sections of the process over. The salt concentrations had to be monitored constantly. Let a solution evaporate too long, the crystals grow improperly. Stop too soon, the separation fails. Timing matters. Consistency matters. She could not take months off, so she taught, raised Irene, processed pitchblende, crystallized radium, measured radioactivity, published papers, all simultaneously. The mental process that can track thousands of crystallizations can also track multiple life demands: compartmentalization, focus, documentation. The same skills. The spectroscopic analysis deserves deeper attention. Eugène de Marseille was the spectroscopist the Curies relied on. He was one of the first to recognize their work was genuine. In July 1898, when they announced polonium, de Marseille examined the spectrum of their concentrated bismuth fraction. He could not distinguish any characteristic lines apart from impurities. This was not favorable to the idea of a new element. But de Marseille noted that uranium, thorium, and tantalum all show spectra formed of innumerable very fine lines, difficult to resolve. Polonium might be similar. The lack of obvious spectral lines did not disprove its existence. By December 1898, when they announced radium, the barium-radium mixture showed clearer results. De Marseille detected 3 new spectral lines belonging to radium. As Marie continued crystallizing, enriching the radium concentration, those lines grew stronger. The barium lines grew weaker. This was visual proof, not just electrometer readings, not just chemical behavior. Actual light from the element, split by a prism, measured by wavelength. Radium announced itself through photons. The 4,533.3 angstrom line became the signature. When that line dominated the spectrum, and the barium line at 4,554.2 angstroms faded to near invisibility, Marie knew the radium was pure. The spectroscope and the electrometer agreed. 2 independent measurements, both pointing to the same conclusion: pure radium chloride achieved. Pierre began experiencing severe pain in his legs and back around 1900. He had difficulty sleeping. His hands cracked and hardened. He attributed it to overwork, to the cold shed, to age. He was 35 when the pain started. By 1904, his hands were so damaged he could barely hold a pen. He conducted an experiment. He taped a sample of radium to his arm for 10 hours. The skin reddened, blistered, took months to heal. The scar remained. He published the results. He noted radium destroys tissue. He did not stop handling it. Marie had burns on her hands by 1902. She called them occupational hazards. Chemists get burned by acids. Physicists get burned by radium. Same category in her mind. The connection to the deep bone fatigue, to the constant exhaustion, to the blood abnormalities that took another decade to establish. By then, the damage was irreversible. The alpha particles from radium decay cannot penetrate skin. External exposure causes burns, but not deep damage. Ingestion or inhalation is the danger. Radon gas, the decay product of radium, is invisible, odorless, and alpha-emitting. Inhale it, the alpha particles hit lung tissue directly, damage the cells, cause mutations, lead to cancer decades later. The shed had no ventilation except the windows. Marie and Pierre boiled radium solutions constantly. The radon released from those solutions filled the air. They breathed it, day after day, year after year. The dose accumulated. The women, called radium girls, painted numbers on tiny watch faces. To get a fine point on the brush, they licked it. Lip, dip, paint. Thousands of times per day. They ingested radium with every brush lick. The radium settled in their bones. Their jaws rotted. Bones fractured spontaneously. They glowed in the dark. Radium jaw. The company denied responsibility, fought the lawsuits. By 1928, the evidence was undeniable. The lawsuit succeeded. Regulations followed. But dozens of women died first. Marie knew about the radium girls. She noted that proper precautions should be taken, but she did not change her own habits. She continued handling radium with minimal protection. Marie died in 1934. The radium girls died throughout the 1920s and 30s. Same element, same mechanism, different timelines. On April 20th, 1902, Marie Curie completes the isolation of radium chloride, 1/10 of a gram. Pure enough to measure atomic weight, pure enough to prove. She publishes the result in Comptes Rendus. The atomic weight is 225. Modern measurement says 226. She was off by 0.4% using a balance in a freezing shed with broken windows and fume-filled air. 0.4%. That is the level of precision the mental process achieves. Thousands of crystallizations, 4 years, tons of slag, 1/10 of a gram, 0.4% error. That is not luck. That is discipline. That is method. That is Marie Curie isolating polonium and radium from pitchblende, because the numbers said they were there, and the numbers do not lie, and someone had to do the work. She did the work. The work killed her. The work changed science. Both are true. The mental process that sees an impossible measurement and says, not impossible, just unknown, that process does not care about survival. It cares about proof. She proved it. The glow remains.